what I'm going to take a look at now is actually are just example problems for these titrations, like what kinds of questions are we likely going to see, and what do we want to be kind of thinking about as we're going through and kind of setting up at these types of problems and solving them. So there's kind of two probably types of problems we're really going to be running into in terms of kind of like what they're really going to be asking. One is going to be like this first one, which is kind of either finding an unknown concentration or figuring out the amount it would take to reach an equivalence point for something. And then the other type is kind of what I have outlined below, and I have two examples for, which is, for a particular titration where they know the concentration of everything that's being used, they're actually just going to have you try and calculate the pH at a bunch of different points in the experiment. So that'll be what we take a look at then next. So for this first example, though, we're asked what is the concentration of a 40.0 milliliter sample of HCl if it takes 25.0 milliliters of 0.5 molar NaOH to reach the equivalence point for a titration. And we have a follow-up part to that, which is would the concentration change if HCl were HF, why or why not, which kind of details like the difference between strong and weak acids, or looks at it, is there any. Now, as a starting point, kind of working this example, I'm going to kind of work this on my whiteboard here in a second. We have 40 milliliters of HCl, and we have 25 milliliters of 0.5 molar NaOH. And it's wanting us to try to figure out kind of what concentration must our HCl have if that's what it took to get to the equivalence point. Well, the biggest thing about all this is really what does it mean to be at the equivalence point, right? And so at the equivalence point, and I'm going to abbreviate a little bit here, the most important thing is that our moles of acid equal our moles of base. And even more specifically, it's really the moles of H3O plus equaling the moles of the hydroxide, right? Just in case it's possible to have some bases that have multiple hydroxides and some acids have multiple protons, like polyprotic acids. And so really more specifically, this is what it means to be at an equivalence point. Now, in this particular instance, we have HCl and NaOH. They both only just have one hydroxide and one proton out of this acid and base, so it's kind of our, for the most part, kind of common, straightforward example where everything's just kind of a one-to-one stoichiometry. Now, to figure out what our initial concentration must have been, we can use the fact that our moles of H3O plus and moles of OH minus need to be equal, right? Because if we're looking at our problem, we can actually find the moles of hydroxide that we're adding to our reaction because we have both a volume and a concentration for the sodium hydroxide. So, for instance, I can then say that my moles of hydroxide should be equal to its volume, which I believe was it 25 milliliters? Yeah, 25 milliliters, so 0.025 liters, times its concentration, which I believe was 0.5, so 0.50 molar. And remember, I can write this as 0.05 molar, but really what this is, if I want to be particular, this is my moles of hydroxide per 1 liter. Right, so look at my units. Like my units are canceling, and I can find my moles this way. So I can just simply take 0.5 times 0.025 or 0.0125 will then be my moles of hydroxide. But since I'm at my equivalence point, when I have that many moles, that means this is also the number of moles of HCl that I must have at that equivalence point. And now if I couple this with the fact that I know what my volume of HCl was to start with, if I want my concentration for the HCl, my concentration should simply be my moles divided by my total volume of my HCl, of the HCl solution that we started with. And so it's not the total of these things mixed together, it's what was my concentration of my initial sample for HCl if I had 40 milliliters of it to start with. So I'm taking the moles of my HCl, which I found. There must have been that 0.0125 moles of HCl present in the 40 milliliters, which is that 0.040 liters. And now I can go ahead and calculate my concentration, which looks like it's about 0.31. If I want to be picky on sig figs, I'm pretty sure we only had 2 sig figs, in this concentration, so probably only 2 sig figs in the HCl concentration as well. So roughly about 0.31 molar would be my final answer. Now, You will sometimes hear people talk about, oh, well, for titrations, you can also do like M1V1 equals M2V2 in terms of being able to do that calculation, which is true. You can do M1V1 equals M2V2, but it doesn't work 100% of the time. It works if it's a 1-to-1 ratio for your acid to base in terms of like one proton and one hydroxide on each of them. But if it's not 1-to-1, like M1V1 equals M2V2 will not work properly. And then you're better off just taking kind of a mole-to-mole approach and thinking about like a balanced reaction and stoichiometry that way to kind of account for that. All right, so that gets us through our first part of this problem. Now, the second part of this question actually asks, would the concentration change if HCl were HF, and then why or why not? So the big difference there being HCl is a strong acid, HF is weak. But the reality is your equivalence point, like if we think about its definition, is just when our moles of acid and base are equal, or moles of H0 plus and OH minus are equal. Well, there's nothing in here that has any effect on whether things are going to be strong or weak. Like even though it's moles of H3O plus, like, strong acid, it'll totally dissociate. But if we have a reaction that's occurring like a neutralization, it doesn't really matter whether it's a strong or weak acid. And so it really makes no difference. The calculation will be the same. If it had been HF instead of HCl, this still would have been the concentration of HF that we started with. There wouldn't have been any difference there. So that's just kind of what I was trying to get at with the second half of this question. Now, the other kind of problem we're going to see for titrations, and I can pretty much guarantee you there will be like a question on your next exam that's going to basically be like this, where it describes a situation that's occurred for a solution, and it's then going to ask you to find pH at various points in the titration. So we'll take a look here at number 2 first, and then we'll look at number 3, which is pretty much the same exact situation, but with a weak acid instead of a strong. Right. So for this first example, we have consider the titration of 35.0 milliliters of 0.175 molar HCl with 2.200 molar NaOH. So we have HCl and NaOH, strong acid, strong base. So the first part, A, is find the volume needed to reach the equivalence point. So it's finding the volume of the sodium hydroxide we're going to have to add since we already have a volume and a concentration for the HCl. So since this is 1-to-1, again, if we want to do kind of like that M1V1 equals M2V2 that I was mentioning a second ago, we can do that and get away with it. Again, I usually like to think of it just in kind of a mole-to-mole relationship of things. I can find the moles of HCl that are present, and then I can convert that, and I know that must be the moles of NaOH I need, and so if I have molarity and moles, I can use that to find a volume. I'm going to go ahead and set this up. I can start with my amount for the HCl that I have. So I can convert my 35 milliliters to liters, 0.0350 liters, and then remultiplying that by its concentration. Right, we had a concentration that was, if I jump back here, looks like 0.175 molar. And remember, that's really moles then of HCl over 1 liter. It's kind of what that molarity is telling us. And now what I can do is I can get my moles, which is roughly about 6.13 to the minus 3. And that's my moles of HCl. And remember, if I'm at the equivalence point, because my goal here is to find the volume of NaOH I need to get to the equivalence point. If I'm at the equivalence point, my moles of HCl should equal my moles of NaOH, because it's a 1-to-1 ratio for that reaction. And now what I can do is I can actually go through and use the moles of sodium hydroxide, which this is the moles of sodium hydroxide I must have at the equivalence point, in conjunction with the concentration of the solution that I'm going to be using to figure out what volume of that solution I need to add. Right, and so if I want to think about how can I do that, well, I can do this kind of just with dimensional analysis to an extent. If I have 6.13 times 10 to the minus 3 moles of sodium hydroxide, I want to get to units of liters, and I need to and I want to cancel my moles of, I want to cancel my units of moles, sorry. And I want to cancel my moles of NaOH in particular. Well, if I want a ratio of moles to liters for NaOH, that's just my molarity, right? That 0.200 molar that I had. And using that, I can figure out how many liters of my NaOH solution I should need. And I think it's about 0.0307 liters or 30.7 milliliters is what we need to add. So that's going to be our volume to reach the equivalence point. For our base, we need to add about 30.7 milliliters of the sodium hydroxide. Now, again, you can do this with M1V1 equals M2V2 in this case. But remember, this equation only works if it's a 1-to-1 ratio, which it is in this case with HCl and NaOH, so that's okay. We can get away with it. Otherwise, it does get a little bit more complicated, right? And for those things that have like multiple bases or stuff like that, this step in here is kind of where that would show up, right? So for instance, if this instead of sodium hydroxide here, it was like calcium hydroxide that had 2 hydroxides, I would actually need 2 moles of HCl for every 1 mole of calcium hydroxide, so that my number of protons and my number of hydroxides would equal each other, which is really what's the things that need to be equal at an equivalence point. Now, I'm not going to show you using the M1V1 equals M2V2 equation. I think that's an equation most people hopefully recognize and can use without too many issues at this point. What I'm going to do is move into the next part of our problem, which is finding the pH after we've added 10 milliliters of base. So all the rest of these, if you don't know how to start them otherwise, I would always just start with the BCA table. Like anytime you're like, here's these, this titration that's happening, my concentrations, volume of my starting solution, find the pH at this point, I would always start with the BCA table if you don't know by just looking. And most of the time, unless you're given some other information, you probably can't tell just by looking. And so it's best to just start with the BCA table and see what you have. It's kind of the safest way to do things usually. So in this case, we're adding 10 milliliters of our base to our solution. And so I'm going to go ahead and set up my BCA table. I'm going to write my reaction. So my reaction in this case, I have HCl plus NaOH, making water, and my sodium chloride, right? And when I set up my BCA table, I want my moles of everything. And this is also why I liked up above figuring out how many moles I was working with for my HCl, because that's my starting moles for HCl. I've already found that now for my BCA table. So 6.13 times 10 to the minus 3. And then for my sodium hydroxide, if I have 10 milliliters that I'm adding, and I had 0.200 molar, I can multiply 0.200 molar times, this will be 0.01 in liters. That's going to give me 2.00 times 10 to the minus 3 moles of sodium hydroxide. And for the rest of this table, don't care about water, just like every other problem for these last couple chapters. And for the sodium chloride, I have nothing to start with. Now, change, remember BCA table, we use the BCA table for these neutralization reactions because they go to completion. So I look at those two reactants, I have less sodium hydroxide, so that's what I'm subtracting from both of my reactants. And this is going to leave me with about 4.13 to the minus 3 moles of HCl left, no sodium hydroxide, and I'm remaking 2.00 times 10 to the minus 3 moles of the sodium chloride. And now, just like all the problems that we saw in the first part of this chapter, like from our last exam, once we figure out how many moles of everything we have left at the end of a BCA table, we want to look at what affects pH. So right now I have 4.13 to the minus 3 moles of a strong acid, HCl, and 2.00 times 10 to the minus 3 moles of NaCl. And again, if you wanted to, you could kind of just ignore the sodiums here, right? The sodiums, and just think about this as ions. That chloride ion is the conjugate of HCl, right? So that means it's neutral. Sodium's always just neutral, it's just a spectator ion. So this over here, even though I have NaCl, the NaCl doesn't do anything to my pH. So all I care about is this right here. I have a strong acid left. Right? So if I have a strong acid and nothing else in my solution, all I should need to find pH is the concentration of my strong acid. Right? So my concentration of HCl is going to be equal to 4.13 times 10 to the minus 3 moles of my HCl that are left over, divided by my total volume at that point in time. And remember, that's what I said was one of the key features of these titrations is always figuring out what's our volume at this point. So in the problem, I started with a 35 milliliter sample of HCl. I have now added 10 milliliters of base. Right? I'm kind of ignoring A. A was a separate kind of calculation. It was, these are not sequential steps. These are just individual parts or different points in the titration we're finding pH. So after adding 10 milliliters of base, if I had 35 to start with, my total volume would be 45 milliliters, right? So I'd have like 0.0350 plus 0.010. And now I can calculate what my concentration of HCl is approximately. And I get about 0.0918 or 0.092 molar. Now if I want my pH, pH would just be the negative log of that. And the negative log of 0.092 comes out to about 1.04. So 1.04 for my pH at that particular point in time. So it's still very low, and that's because I still have mostly just a strong acid in my solution. And I did start at a reasonably high concentration at 0.175. Okay, the next part. Part C, we're going to look at the pH of the equivalence point. So for question 2, part C is the easiest part of all of this. Whereas when we get to question 3 here in a second, part C is actually going to be the hardest part of all of that, unfortunately. So we're looking at this pH of the equivalence point. Well, what am I reacting? It's a strong acid and a strong base, right? We said earlier, if it's a strong acid and a strong base, if we're at the equivalence point, the moles of each of those are equal. And if they're both strong, they're, conjugates are neutral. So all I should have is some neutral salt and water. So my pH is just 7. That's it. So part C, my pH is just 7 at the equivalence point. But only because it's a strong titration. Right, when we get to question 3 in a second, that's not going to be the case anymore. I'll label kind of my parts of our calculation here that we've been doing. All right, and then the last part for number 2 anyway, and I keep kind of coming back here. Let me show this here, make sure I have this step shown on here. I keep turning to my screen and I'm not sure if I'm actually showing it. So kind of rehash real quick what I had up here, right? I had my BCA table that I was filling out that had all of my moles of everything that I was kind of putting in. And then I had my, found my concentration of HCl, 0.092, found the pH, 1.04. And then I said part C there, my pH is 7 at the equivalence point. So sorry if I cut any of that off with the problem screen on top. Now, as I move to part D, I'm going to be looking for what's the pH after I've added 5 milliliters of base past the equivalence point. So on this part, I have a way that I can kind of skip the BCA table because if I'm thinking about what it means to be at the equivalence point, that means all of my HCl and all my NaOH are gone. But then if I add 5 more milliliters of base, the only thing that's going to be in my solution at that point that matters in terms of pH is NaOH. And if I go back to my BCA table for a second and kind of show what I mean by that, if I'm past the equivalence point where I have excess sodium hydroxide left over instead, this other product was just a neutral product. It doesn't matter to pH. So the only thing that matters is just going to be this strong base. So however many moles of my NaOH I have kind of in excess should be, what I need to find my concentration of hydroxide and then my eventual pH. And so that's actually how I can approach this problem. So since we're past the equivalence point, this means that my hydroxide is in excess. So NaOH is only species in solution that impacts pH. So as long as I know my moles of NaOH that are in 5 milliliters, which I can find using its concentration, I can find the moles of NaOH that are there, and then I can divide by what my total volume at that point in time would actually be, which would actually use our answer to part A of this question that we've already found, to then go back and figure out what my concentration is to get eventually then the pOH and the pH. So to show all of those kind of in our steps here, if I have 5 milliliters, that's 0.0050 liters, times for the sodium hydroxide, it was 0.200 molar. Right, I end up seeing here that if I multiply these things together, I get about 1.0 times 10 to the minus 3 moles of NaOH. And so this is what's left. right? If I'm 5 milliliters past the equivalence point. And now what I want is my concentration of sodium hydroxide, which is going to be equal to 1.0 times 10 to the minus 3 moles divided by my total volume if I'm 5 milliliters past the equivalence point. Well, if I go back and look at my problem, I started out with 35 milliliters of HCl. In part A, I found what it took to get to that equivalence point. So if I hadn't done that part of the problem already, I would basically have to do everything that I did in part A up here. I would have to do this again as part of this problem. But since I've already done this, I know it takes 30.7 milliliters of sodium hydroxide to get to the equivalence point, and then I went 5 milliliters past that. So my total volume right now would be 35 plus 30.7 plus 5 milliliters. Right, so if I scroll back down, if I'm going to put everything in liters, I have 0.0350 liters from the starting acid, 0.0307 liters, that's what I added to get to the equivalence point, and 0.005 liters that I have now gone past the equivalence point as part of this problem. And now I can put all of these pieces together and I can calculate what my concentration should be. And I get a concentration of about 0.014, we'll just probably leave it at 2 sig figs there, molar. And that means if I want to find my POH, I can just take the negative log of that. And so my POH comes out to about 1.85, which means my pH should be 14 minus that. It's going to be about 12.15. So 12.15 would be my pH, that distance past the equivalence point. Now, what I want to kind of move into with the last question of this is basically looking at this exact same problem in terms of all of the concentrations and volumes and everything, but how much of it actually changes if we have a weak acid instead. And you'll note that for these different problems here as part of parts of the titration, if I kind of scroll back up for a second, part B was the only one I really did a BCA table for. Part C I didn't need to because it was strong reaction, and I knew my pH was just 7 at the equivalence point. I don't get that lucky in my next example. When I have a weak acid or base involved, then the calculation for part C gets very different. The calculation for part B is similar, but just in the last step to find the pH, or the last couple steps to get the pH, will be a little bit different because we won't have just a strong acid left. We'll actually end up with a buffer when we look at it in a minute. But the good news here, for question 3, parts A and parts D are actually going to end up pretty much the same. Right? This is the exact same question, we just now have a weak acid. So this is acetic acid that's 0.175 molar. I'm going to have a Ka value for it that they give us. So the volume of the base needed to reach the equivalence point. Remember what our first question was. Does it matter that we have a weak or a strong acid to get to the equivalence point? No, it doesn't. So for question 3, A is going to be the same answer that we had previously. And so I'm going to, on my whiteboard page here, for question 3, part A, I'm going to say same as 2A, which was basically just that we figured out that it took 30.7 milliliters of NaOH to get to the equivalence point. And again, if you want to do M1V1 equals M2V2 here to find that, you can, right? Acetic acid and sodium hydroxide would be a 1-to-1 ratio. Like acetic acid is 1 proton, sodium hydroxide is 1 hydroxide, and that's what I really mean by a 1-to-1 ratio there. And so now for part B of number 3, it's going to start out very similar to what I had in my previous BCA table, except that it's going to be a little bit different now that I have my acetic acid. And I'm going to write this the way I usually write acetic acid, which is this, plus my hydroxide. I'm actually going to leave the sodium out this time because that's what I normally do. Making water and acetate. I think it's easier without the sodium there to kind of see your conjugate pair that you're going to be making. And now to put in my amounts, the nice thing here, my moles for acetic acid should be the exact same that I had for HCl in the last example, which was that 6.13 times 10 to the minus 3. right? And normally you just get that by taking your concentration and your volume, multiplying them together to get your moles. Hydroxides, the same exact situation, right? For part B, we're 10 milliliters of base that we've added. We have 0.2 molar NaOH again. So I can go ahead and take 0.2 times 0.010, which will give me 2.00 to the minus 3. Don't care about water, don't have any acetate yet. So minus 2.00 to the minus 3 for my change on my reactants, same as before. Plus that amount for my products, and this will be important this time. Like last time we kind of got away with ignoring that because our product was just a neutral salt. That is not the case this time, right? So I get to my after part of my BCA table this time, having started with the weak acid, and I find that I have about 4.13 to the minus 3 moles of acetic acid and 2.00 to the minus 3 moles of acetate, right, the conjugate base. And this is why I left the sodium out. It's just easier to see, hey, this is only different by a proton than this. This is a conjugate pair. If they're both there pretty similar amounts, that means I have a buffer, right? It's kind of the first part of chapter 17. And so now if I want to find pH, the fact that I have a conjugate pair means I have a buffer. And if I have a buffer, that means I can jump straight to our Henderson-Hasselbalch equation, if I can talk. So my pH is now pKa plus the log of the base over the acid. Yeah, if I can write, there we go. And plugging in our pieces, pKa, negative log 1.8 times 10 to the minus 5. That's our Ka of the acetic acid. Plus log of the base. And remember, we can just use the moles rather than concentrations here because they're all in the same solution, so the volumes would be the same anyway and cancel out. So 2.00 to the minus 3 over 4.13 to the minus 3 for my moles. And now I can calculate what that pH is going to come out to. And I get a final pH here of about 4.43. So pretty different pH here, after a partial dissociation. Kind of a big difference between the weak acid versus the strong acid, right? The strong acid, we had a much lower pH because it was a strong acid. And all we had left at that point was the strong acid. Here we have a buffer, a little bit different situation. Now, for the next part of this problem, if I want to move into part C, I have a couple things I can kind of keep in mind here. So I can make a BCA table to start this part. And if I'm at the equivalence point, the kind of thing that I would basically know is that if I make another BCA table for this, so I have my acetic acid plus my hydroxide, water, and acetate. If I have 6.13 to the minus 3 moles of my acetic acid to start with, at the equivalence point, that's the number of moles of the hydroxide I must be adding. Right? I want them to basically completely neutralize each other so that neither one of them is left. But I have to pay attention to my product side here because I have a product that's not neutral in terms of pH. Right? I have the acetate ion, which is the conjugate base of my weak acid, which means it is a weak base itself. So this acetate ion that's left over here, being a weak base, means if I look at what's left in my solution at the end of this BCA table, it's just a weak base. And if I think, all right, well, how do I find the pH of a weak base solution? It's always an ice table, right? Instead of a BCA table because it's an equilibrium now. And if I have a weak base, what's the reaction that's going to happen? Well, if I have only a weak base in solution and it's all in water, now what I need to do is write a reaction of that weak base in water. And this is an equilibrium. And since it is a base, one of my products has to be hydroxide because it's going to pull a proton off the water. And that means my other product is going to be acetic acid again. Now, since this is an equilibrium, it is the ice table. And there's two things I have to be careful about here. One, if it's an ice table, I can't use moles. I actually need concentration. So before I can even start using this ice table, I have to get this this number of moles into a concentration. So my concentration of acetate should be equal to my moles that I found up above, right? That 6.13 times 10 to the minus 3 moles divided by my total volume at the equivalence point. Well, I had 35, and this actually, let me fix this typo. I didn't catch this here. It should be milliliters in both of these. Apologize. And so I had 35 milliliters of my sample that I started with of my acid. And if I've added, remember in my part A, I found how much it took of the base to get to equilibrium, to the equivalence point. And in my work, we said up above that it took 30.7 milliliters. Right, so 30.7 milliliters to get to the equivalence point. I had 35 milliliters of acid already. So that means my total volume at that equivalence point should be 0.0350 plus 0.0307, right, 35 milliliters plus 30.7 milliliters. And now I can calculate that concentration. So if I calculate that real quick, I get about 0.933 molar, or we could just, oops, I left out a zero there. 0.0933, or 0. Or you can say like 9.3 times 10 to the minus 2 if you want that way as well. Now, at this point, why that's important is that's what I'm going to come back and put now into my ice table, right? Because now I'm going to figure out how much of my acetate is going to kind of dissociate back to give me some of my acetic acid. And in this one, it's got to go forward. I'll minus x, so 0.0933 minus x, plus x, plus x, x and x. Now I can make an expression, to try and solve for these x's. But remember, this is for a base, right? If I look at my problem, I don't have any KBs. All I have is a Ka for my acetic acid. So for me to set up this reaction and be able to solve it with an equilibrium constant, I actually need the Kb because the reaction itself we're looking at is making hydroxide. So how do I find that Kb? Well, remember, for any conjugate acid-base pair, Kw is Ka times Kb. So in our case, Kb should be equal to Kw over Ka. Kw is 1.0 to the minus 14. Ka 1.8 times 10 to the minus 5. This is going to be then about, what does that come out to? Guessing about 5.6 times 10 to the minus 10, if we calculate that for our Kb. That's now my equilibrium constant for that ice table that I just set up. So I have this Kb. There's my equilibrium constant. That's going to apply to this ice table, which I'm now going to have x times x over 0.0933 minus x is the other half of that equation. But I can definitely, in this case, use x as small as an approximation, so I can ignore that minus x to make my math here at least a good bit easier. And then I can solve for my x value, and I get x is about 7.22 times 10 to the minus 6th. And now I have to think back to, well, what was that x, right? In my ice table, if I go back up a little bit, x is actually the OH minus concentration. So still have a couple steps left here. This is my hydroxide concentration, which means my POH is the negative log of that. And so if I take the negative log of that, I get a pOH that's about 5.14 roughly, which means my pH is going to be 14 minus that, which is going to then be about 8.86. So this was a lot of work to get this equivalent point pH. And this is why I was saying kind of earlier, in these problems, the equivalence point pH is either really, really easy if it's a strong, strong titration, or it's probably the longest, kind of hardest example we're going to see of any of these titration problems if it's a weak, strong combination. Because look at all the things we had to do here. We started with a BCA table, right, where we set the moles of the acid and base equal, because that's what it means to be at the equivalence point. Now, I will kind of point out one thing. This first BCA table, if you're at the equivalence point, you can kind of almost skip this first BCA table if you recognize that you have the starting moles of acid based on your concentration and volume given. That basically tells you how many moles of base are going to be left, the conjugate base should be left at that equivalence point, because there isn't going to be any of the starting acid and base that are neutralizing each other at the equivalence point, because that's the whole point, right? At the equivalence point, those two things are equal. They're both completely gone. So all we have left is the conjugates. So we have our acetate ion here that's still left over, which is a weak base because it's the conjugate of a weak acid. And now in order to use this weak base, if it's just a weak base to find pH, we need an ice table, but it's an ice table that's going to be making hydroxide because it is a base, which means I need a Kb. So, and I also need concentrations instead of moles. So I have to find the concentration of my base itself that's left over, then use Kw and the Ka value for my acid to find the Kb for this conjugate base that was left. Then I could solve the ice table for my X and eventually get my pOH and my pH, right? So that's a pretty lengthy process to get that pH at the equivalence point. And that's why I said it's, by far the most difficult part, I think, of any of the titration examples is the equivalence point at, what's the pH at the equivalence point for these weak, strong titrations. But the good news is it's going to be kind of that same thing every time. So once you work kind of just like 2 or 3 examples of this type, it does get a lot easier because it is going to be the same general process. And once you've worked a couple of examples and kind of thinking about equivalence points, you probably don't even need this first BCA table. You can almost just start right here, so that then you can go right to your ice table once you get your concentration. And now you're really just looking at solving like one ice table and being careful because it's a base and not an acid. And that's not as bad. But it is still a good number of steps. It's really easy to make mistakes. One of the most common ones I see for people that they get to the ice table, they get the concentration, but then they forget that they really need a Kb and not a Ka, and so they forget to make that change. That's one really common mistake I see on this one. Or they get to the very, very end and think X just is the H3O+, but remember in the ice table here, it's, again, Kb, so we're getting hydroxide, so you have to do that last extra step. So a couple things with that. One good check to always think about when you get to the very, very end, if you started with a weak acid and a strong base and you're at the equivalence point, you need to have a basic pH, right? Because what's left is your conjugate base of the weak acid, so your pH better be bigger than 7. And when we got to the very end of this problem, our pH was 8.86. That's bigger than 7. Right? If you'd forgotten to do this last step and thought X just was the H3O+, you'd have 5.14. That should hopefully trigger a quick alarm like, hey, that's not the basic pH I was expecting. It's like, oh, that's because it's the hydroxide concentration, that's the pOH that's 5.14. And so you can kind of use that to help reason through some things there for that. But I'm going to cut this video off here. I think this has been probably long enough, kind of going through a couple examples here. You can kind of already see how some of these problems can get a bit lengthy. But there's nothing really terribly new, I think, in terms of what you're doing. It's still very much do a BCA table, see what's there, similar to what we were doing at the start of Chapter 17. And so when you look at kind of some of the homework problems and kind of the daily assignment problems for this section, it's still going to be following a lot of the same things that you've already been doing. And again, the equivalence point one is the tricky one, but pay attention. If it's strong, the equivalence point is easy. But if it's that weak, strong, then you're going to have some work ahead of you. Just kind of be aware of that. And it's probably a good hint there, too, if you're working a problem on my test and it's asking for the pH of the equivalence point and it's only worth like 2 or 3 points, that's probably because it's a strong titration and the pH is just 7. But if it asks for the pH of the equivalence point and it's worth like 8 or 9 points, that's probably because it's a weak, strong titration where it's going to take some work to get to that answer. It's probably just another good heads-up clue maybe you can do, kind of look at and pay attention to, like while taking a test to kind of see some of those things. But this time for real, I'm going to kind of wrap up this video here. We'll have a little bit more here for chapter 17 on solubility in our next couple videos to kind of wrap up this module.